thank you very much, Professor Paulo Colombo. He has been an inspiration for me about ceramic additive manufacturing, and it's a great pleasure to have him here. Right now, I'm going to give some instructions about the contests that we have here in the event. I will give the instructions both in Portuguese and in English. So I will start in Portuguese, give all the instructions, and after that I go to English, okay? So starting in Portuguese. Bom, pessoal, a gente vai ter... a gente já tinha divulgado que a gente teria 2 prêmios aqui no evento, que seria do melhor pitch e da melhor pôster. Esses 2 prêmios estão mantidos e a gente vai ter 2 prêmios adicionais. Então, esses prêmios iniciais eles vão ser julgados pela comissão avaliadora e, além disso, vocês vão poder votar tanto no pitch quanto na apresentação que vocês mais gostaram. Então, no kit de cada um de vocês tem uma cédula, melhor pôster e melhor apresentação. A gente sugere que vocês façam o seu voto apenas amanhã, após terem vistas todas as apresentações, e vocês vão estar colocando lá numa caixinha que a gente vai destinar para isso amanhã, tá bom? Com relação aos prêmios previamente divulgados, a gente já tinha algumas regras, elas já estavam estabelecidas e eu só vou relembrá-las para vocês. Então, no prêmio da JEX, da European Ceramic Society, vai concorrer pitches que já foram escalados, né? Apenas pitches apresentados em inglês e que tenham os requisitos que foram pré-estabelecidos. Então tem que ser estudante ou estudante de graduação, técnico e tudo mais, e que tenha concluído nos últimos 2 anos. Então, por exemplo, professor não vai estar concorrendo nem no prêmio da JEX, nem no segundo prêmio que a gente tem de pôster, que é da CeramicAM, que são prêmios destinados exclusivamente a estudantes ou recém-formados. Por outro lado, nos prêmios da votação popular, está todo mundo concorrendo, tá bom? Então, podem ficar tranquilos. Com relação à premiação, já tinha sido divulgada. No JEX, a gente tem 600 euros, mais a inscrição de um congresso, que vai ser do EESC-USP, na Europa. Da CeramicAM, a gente tem a filiação por 1 ano, mais a inscrição no congresso do ano que vem. E em todas os 4 prêmios a gente tem peças lindas que foram produzidas pela Dura Printer e elas estão inclusive expostas lá no stand. Então sugiro que vocês passem lá no Coffee Break e dá uma olhada no que vocês estão concorrendo, certo? So in English now, so basically we have announced before 2 awards, one for the best pitch and the other one for the best poster presentation. We are keeping these posters, and we also have 2 other prizes for the same things, but not chosen by the academic committee, but chosen for you all. So in your bag that you receive, you have 2 cellulose, I don't know, and over there you can sign tomorrow which of you thought it's the best poster presentation and the best pitch presentation, okay? So for the regular prizes that are going to be judged by the committee, we are considering just presentations in English and from people that are not professors, so basically students or people that have graduated in the last 2 years, and also the people from JEX that are here, they are presenting the pitch, but they are not competing in this category, and they are helping to evaluate, right? So I think it's pretty much it. Any doubts? So let's start with the first pitch presentation. So each pitch has 3 minutes. Each pitch has 3 minutes. Over there, we will say when we have 1 minute left and when it's over, okay? So I would like to ask the first one, that is Daria.
Sorry. Okay. But it's still here, but not there.
Oh, okay. Maybe you need to give a presentation on that.
Okay. Hello, everyone. Sorry for this small delay. My name is Daria. Yeah. Oh.
Yeah, it is.
Okay. Sorry. Hello, everyone. My name is Daria Chernomorets, and today I'd like to introduce shortly my work about optimization of the direct ink writing process for obtaining transparent ETS ceramics. It's shortly about me. I'm from Italian Institute in Faenza, and also I'm PhD student in Institute for Single Crystals of National Academy of Science in Ukraine in Kharkiv. So ITRIA transparent ceramics is a widely used material. It can be used as infrared transparent optical windows, laser host materials, domes, etc. And it's possible because of good optical and mechanical properties and also high thermal and chemical stability. To ensure these properties, there are some requirements like high density of samples, also absence of defects as porosity or secondary phases. It's very important for such materials since these defects are centers of light scattering, so it leads to deterioration of optical properties, so we should avoid it in any case in our samples. Speaking about direct ink writing of transparent ceramics, actually not a lot of works are presented about it, especially about ITRIA. For the moment, only one published paper about it, and it was done recently, this summer, and it can be explained very easily. This process is very challenging. Among the most important challenges is that we should obtain stable and printable ink, having a high solid loading, and also uniform nano-sized powders. Together it's almost impossible. Also high viscosity with full deforming and drying is very hard. So we should optimize rheological properties of these slurries to obtain transparent ITRIA ceramics by vacuum sintering. We optimized composition using dispersant binder, solid loading, and humectant, and obtained printable ink. And as a result, we obtained ITRIA ceramics with such microstructure. To discuss all details and main results, I invite you to poster session today. We can speak more about it. Thank you for your attention.
Thank you very much, Daria. And now I would like to invite Fernanda. And I would like to remind the reviewers to give grades.
Já começou? Bom dia, meu nome é Fernanda, eu faço Engenharia de Controle e Automação e nesse primeiro encontro CeramicAM será apresentado o desenvolvimento de manufatura híbrida por cerâmica e, bom, dessa forma a gente vê que esse estudo partiu do desafio em ligar a cerâmica ao material metálico, que dessa forma recebeu uma ligação covalente com o material de transição. O material cerâmico ele é muito utilizado na indústria aeronáutica, devido à sua resistência ao calor. Ela é aplicada em câmaras de motor foguete e palhetas de turbina, funcionando como barreira térmica. O material de transição foi o nicraoli e o cerâmico a zircônia. E com a ajuda do sistema de laser cladding controlado por um braço robótico e programado e guiado por programação, foram estudados métodos de deposição, utilizando 3 etapas, que a primeira é a deposição desse nicraoli, o revestimento. A segunda é a regularização dessa superfície com procedimentos mecânicos, e a terceira, pelo feixe do laser, é feita essas estruturas de quadrículas, que na escala de 1 a 1 milímetro de espessura e 100 microns de profundidade. Esse experimento foi repetido 3 vezes em busca do melhor parâmetro e depositado a zircônia. No melhor parâmetro foi crescido esse revestimento, essa base ela sofreu o crescimento. E de acordo com a análise de raio-x, foi comprovada a ligação covalente e bom aspecto na densificação da zircônia. Então, conclui-se que essa metodologia é promissora, porém ela precisa ser aprimorada, explorando novos parâmetros. Muito obrigada.
Thank you very much, Fernanda. And now I'd like to invite Marlon.
Hi everyone, first of all, good morning and thanks for the presence for everyone. Now I make this presentation about additive manufacture to use for CeramicAM to ballistic improvement. First of all, you know how it's difficult to use different types of materials to ballistic improvement. The common materials is fibers and another materials because of the weight of these materials, and ceramics now is used to broken the bullets in the impact. And the common way to produce this ceramics is a common way. You sinter this silicon carbide, and you can use this. This another way is using additive manufacturing to transform this silicon carbide, but it's hard because you know after you use additive manufacturing, you have these steps. You need to sinter this material, and this process you need high temperature. This is the challenge, and you have some ways, some process, then you can have a new role to change this. Now I present the best ways to use to produce silicon carbide protections to bulletproof. The first of all is FDM. You know, at the end, the Professor Colombo showed is a nice way to produce. This process is common to produce polymers, but now you can use this to produce silicon-carbon ceramics too. The second is DLP, you know, the digital light processing. The another one you can use is stereolithography. Another is two photon polarization. Injector is another one that you can produce realistic too. Direct ink printing, SLS and SLM, and DD is another way to produce the ceramics. This bibliography show this is the best way to produce ceramic through protection. Thanks for everyone.
Thank you very much, Marlon. Now I would like to invite Anderson.
Well, hello there, I'm Anderson. I'm working in a project to convert CO2 to methanol through heat and pressure using rhenium-doped titanium. And my research specifically is to produce this titanium paste to print the reactors through extrusion method to direct ink writing. And we are basically using titanium powder in the ammonium perrhenate solution. The ammonium perrhenate is for the doping material. And the issue we have is that the ammonium perrhenate, the rhenium actually, as a doping element, it starts to evaporate from the surface of the titanium at a relatively low temperature, at 250 degrees. So how can we have like a solid piece without reaching the sintering temperature of the titanium? The solution we got is to use the Pekin resin. It's a polymeric precursor of oxides, so you have like a polymeric chain with the cation of your metal that you turn to the oxide. And how it's working in our paste. First, this resin works a rheological agent, changing the rheology and making giving viscosity to the paste. And after drying, it keeps the green part in shape, keep the shape. After burning at relatively low temperature, we can burn it like in 350 degrees. The polymeric resin will start to burn and turn into the titanium in this case, forming nanotitania. This nanotitania will work as a binder, like gluing the titanium powder that's already in the suspension. So we could get solid pieces, as you can see here, sintering at 350 degrees. That's it. Thank you.
Thank you very much, Anderson. And now I would like to invite Enzo.
Is this close enough? This is the very first time I speak in a microphone like this. So I hope it's enough. Let's select. Italo, would you give me some help with the PDF file, please? Someone from the staff. There it goes. Good morning, ladies and gentlemen. I'm Enzo Todeschini, and I am a mechanical engineering undergraduate student at the São Paulo State University. I work under the supervision of Professor Cesar Renato Foschini, and today I had the great pleasure to bring two different contents to present you. So there are two different posters which will be shown. I've worked on this project for the past 4 years, during which time I had the opportunity to design a extrusion system for direct ink writing. So the project began when I could barely calculate the derivative and took 4 years to develop. The first design is called SEPGI3. Unfortunately, the name doesn't sound so good in English as it sounds in Portuguese. In Portuguese, it is CPG3. So this very first model had wonderful capabilities, but during the commissioning efforts we found several design flaws that needed to be corrected. So the poster we are presenting today regards the optimization process from the CPG3 to the Lazarus system, which is the actual system we use today. It maintains all the capabilities of the former systems and corrects the previous flaws. So once we built the Lazarus system, we needed to understand its capabilities. We needed to characterize its performance. So we've made a model that combined Taguchi's design of experiments with dimensionless numbers, which are commonly used in heat and transfer calculations. And this model is highly efficient. We achieved a 96% reduction of the experimental effort necessary to optimize the model. We took 3,645 measurements in less than 10 hours and with minimal material consumptions. And given this characterization effort, we have the model that describes the geometry of the 3D printed filament using direct ink writing, thank you, as a function of several important process parameters. As you can see, this equation is an implicit equation, so you can also make the reverse work and see, look, I need a filament which has a given width, so what are the best process parameters to generate this width? So I invite you all to come and check both posters. They look like this, and one of them is going to be presented in the morning, and the other is going to be presented by this afternoon. Thank you very much for your attention.
Thank you very much, Enzo. So right now we can go to the coffee break section. Over there we are having 11 poster presentations. So keep in mind that every single one of you can vote tomorrow for both best presentation and best poster. I also would like to thank again all our sponsors, and especially for this coffee break, it's provided by 3D Ceramic. So thank you. Então, obrigado a todos. Agora o coffee break está aberto. Aproveitem e agradeço ao patrocinador 3D.